All right, we should know the derivatives of all these functions on the list. Notice the grouping of the 6 trig functions. All your life, your calculators have had the 3 trig functions sine, cosine, and tangent. They haven't had secant or cosecant or cotangent, sine, cosine, and tangent. However, there's a better way to think of your 3 main trig functions. Think of sine and tangent and secant. Why would I encourage you to do this? Because think of these red ones as the co-functions, co of the sine, co of the tangent, and co of the secant. If you know these 3 derivatives, then to get the derivatives of their co's, for example, the derivative of cosecant would be just memorize secant's derivative. And for the cosecant derivative, take the opposite sign and make this a cosecant and cotangent. Works for all the co's. Cotangent's derivative, what was tangent's derivative? Secant squared. So for the cotangent's derivative, do a negative cosecant squared. All right, let's come down here to the bottom. We all know that e to the x's derivative is itself, and natural log's derivative is just 1 over x. But did you know that it can also be thought of as just one rule, whether it's base e or base a? The rule is 1 over natural log of the base times the base to the x. That will always work for derivatives of logs. It just so happens that for the natural log, that's base e. So if we use this rule, it's 1 over natural log of base e times base e to the x. And that's 1, so we just get 1 over x. ln x's derivative is 1 over x. The same thing's happening here. There's really just one rule. The derivative of an exponential function like a to the x is natural log of the base times itself, a to the x. Well, when the base is e, natural log of the base is 1. And then the base to itself, we get e to the x. All right, have all these memorized. Now look at the green check marks. And the green check marks mean that we have proved all of these in class or in your homework, or if neither of those, we should be able to prove them all. The only one we haven't proved is maybe the simplest derivative formula, but maybe the hardest one to prove. Maybe some other time. All right, next slide. Well, let's take a look at how to find some of these derivatives, just to make sure everybody's on the same page and is able to do them. But before we do, in order to derive these formulas, we need the chain rule. So let's go to the chain rule next. Well, the chain rule is essentially finding the derivative when you have a composition of functions. So if y is f of g of x, then find dy dx. Once again, I strongly encourage you to make a quick sketch. This black curve could be the composition f of g of x is equal to y. Well, we're going to find the derivative at x, dy dx at x, and so we need a secant segment. So put another point over here at x plus h, draw the secant segment, find the slope of that using the slope formula, and then find the limit of that slope as h becomes 0, so that our secant segment becomes this instantaneous slope of the curve at x. So the slope of this segment right there, and what's the limit as h approaches 0? All right, this is one of those proofs that will use a clever little algebraic trick. Let's multiply by 1 so we don't change it in the form of g of x plus h minus g of x over itself. Let's go ahead and rewrite this denominator as just h, canceling out the x's. All right, next we're going to use the commutative property of multiplication to rewrite the order of these denominators. We're just going to flip the h and this denominator, change places. All right, so the h goes there, and this difference goes there. And now look at what we have. We have that the derivative of this composition of functions is the limit as h approaches 0 of the product of these two rational expressions. Well, a property of limits says that the limit of a product is the product of the limits. So we'll rewrite this as a product of two limits. All right, now look at what we have. We should recognize this as the derivative g prime of x. And you recognize this limit as h approaches 0. Notice that's just a difference quotient for the composition of functions f of g of h. So the output value f minus the output value f. So this is y2 minus y1. And then f's input, which is essentially the x-coordinate minus the x-coordinate. That's just a slope formula. This is f prime of that input. As h goes to 0, that input is going to g of x. So this is f prime of g of x. And there we have it. The derivative of a composition of two functions is the derivative of the outside function multiplied by the derivative of the inside function, the chain rule. Now this proof only works when g of x plus h and g of x are not equal to each other. And that's pretty much every case we'll ever consider. But if you want a proof for when they're equal to each other, then you'll have to check an appendix in the textbook. But I don't know that anybody's going to want to look that up. So let's call it QED. All right, so now we can do a nice rigorous derivation of all of these formulas. Let's start with the cosine using the derivative formula. And then we need to use an identity for the sum of two angles with cosine. And you don't have to have that one memorized, but it is on the inside cover of your textbook. It's that. And then we'll regroup the cosine with this first term, factor out the cosine, and this is a limit that we know goes to 0. So for this first term, that goes to 0 times cosine of x, which is 0. And for sine of x sine of h over h, we can think of the sine of h over h separately. As h goes to 0, we've proven that that goes to 1. So 1 times sine of x is sine of x, 0 minus sine of x, negative sine of x. There's the proof. All right, let's look at another one. How about a to the x? So to find the derivative of a power expression, or an exponential expression, we let y equal a to the x, get x out of the numerator, or out of the exponent, by taking the natural log of both sides, and then take the derivative of both sides. So the derivative of this side is with respect to x is 1 over that expression times dy dx, chain rule. And on this side, remember ln of a is a constant. So a constant times x has a derivative of just that constant. All right, then when we solve for dy dx, we multiply both sides by y. Remember y is a to the x. So the answer is the natural log of a times a to the x. Okay, how about log base a of x? We do that same strategy, let y equal log base a of x, then let's find the derivative with respect to x of everything here. Well, before we take the derivatives, let's get rid of the log by doing the inverse function of log base a, the exponential function base a. So we have a to the left side and a to the right side, and the exponential function and log function of the same base cancel each other out, so they leave us with x. Now do the derivative with respect to x of some real number raised to the power of y. We're going to have to use our rule that we just developed for the derivative of a to the x. It's the natural log of that base times a to the x. So here the derivative of a to the y is a natural log of that base times a to the y. But we have to use the chain rule. So times dy dx. And the derivative with respect to x of x is 1. All right, so dy dx equals 1 divided by the factors natural log of a and a to the y. But a to the y is just x, so we can just put x for a to the y. I guess we didn't need that because a to the y is just x. There it is. That's the derivative of log base a of x. All right, so I think there's one more on this page. Yeah, tangent, we just used the reciprocal identity and then the quotient rule. And that quickly runs the course to tangent's derivative being secant squared. So now we're going to take a look at our derivative formulas, but when it's in terms of another function of x. So these will be using the chain rule. So it's just the same formulas that we know, but then with the chain rule, if u is a function of x, we have to multiply by u prime of x. Okay, next, derivatives of higher order. All right, some of those definitions or some of those notations: y equals f of x, y prime equals f prime of x equals the derivative with respect to x of y, or just dy dx. The second derivative, f double prime of x, will take the derivative with respect to x of the first derivative, and we get d superscript 2 of y over dx superscript 2. Third derivative, we can use 3 tick marks again, but when you get to the fourth derivative, we're not going to have 4 tick marks, so we'll just use 4 in parentheses. It's not an exponent, it's the order of the derivative. The fourth derivative of y, fourth derivative f of x, and the fourth derivative of y with respect to x. Oops, that should be a 4 right there. And then the nth derivative of y, the nth derivative of f with respect to x, the nth derivative of y with respect to x. N times. So there's the notation of your higher order derivatives. The first function could just be like a position in certain scenarios, where if it was position, then y prime would be the velocity, the change in rate of y with respect to x, like distance with respect to time. And then the second derivative would be acceleration, the third derivative would be jerk, the fourth derivative would be snap, and I don't know what comes after that, but those are some physics words. Okay, moving on. Roman numeral 4. Implicit generation. Wait, implicit what? Implicit differentiation. These are the guidelines. We're going to differentiate both sides of an equation with respect to x. Then collect all terms with dy dx on one side of the equation and solve for it, which often involves factoring. All right, let's see 2 quick examples. Find the slope at any point on this circle whose center is 3, -2. First, we'll need the equation of the circle. If it was centered at the origin, it would just be x squared plus y squared equals r squared. But it's not centered at the origin. It's centered at 3, -2. So we had to move 3 to the right and 2 down. There's our translation, 3 to the right. And for the center to come 2 down, this change will affect that translation. And the radius, you can see, is 3 units in every direction, so this will be 3 squared, or 9. All right, so what is the slope of this circle at any point? Let's find the derivative. Slope will always be dy dx, so we need to find dy dx. So we are going to start by taking the derivative with respect to x of the entire equation, which means the left side and the right side. So the derivative with respect to x of the left side, 2 times x minus 3 to the first power, plus 2 times y plus 2 to the first power, times the derivative of y, and that's using the chain rule. And then the derivative with respect to x of 9 is 0. All right, so this is the first step in implicit differentiation. Now we just need to solve for dy dx. So let's subtract this entire term from both sides, and then we'll divide by this black factor. Here we go. We subtracted that from both sides. Now we'll divide by 2 times y plus 2. And we have our final answer. The slope at any point on that circle is equal to, and the 2's will cancel out, and we can take the opposite of x minus 3 and say 3 minus x. 3 minus x over y plus 2. And there it is, the slope of the circle using implicit differentiation. Let's do one more example. Let's find the derivative with respect to x of this expression. You could go ahead and try the quotient rule, low d high minus high d low over low squared, the square root of x squared plus 1 times 2 times x minus 2 minus x minus 2 squared times 1/2 of x squared plus 1 to the negative 1/2 times 2x, then all divided by this squared. We could do that. The quotient rule would give us this, and man, that looks horrendous. Can we simplify it a little bit? guess we could stop here, or we could get rid of this complex fraction. Complex fraction means a fraction within a fraction, by multiplying by the square root of x squared plus 1 over itself. Now we have no fractions in our numerator, but this is just kind of ugly. Not really crazy about this. Let's do this problem a different way. And keep in mind that when you're taking derivatives of complicated rational expressions, it's probably going to be a lot cleaner if you rewrite this first. How would we do that? Using properties of logs. Here we go. All right, let's let y equal this blue expression. And if we're trying to find the derivative with respect to x of the blue expression, it would be the same thing as finding the derivative with respect to x of y, dy dx. I've changed the square root to a fractional exponent, and now let's begin. The way we're going to simplify this is using logarithms. So we'll take the logarithm of both sides. And now we have an abundance of logarithm properties that can allow us to rewrite the right side. Take a look. So the logarithm of a quotient is equal to the difference of the logarithms of the numerator and denominator. And then we know we can put this exponent in front of the natural log. Same thing with this 1/2. All right, that's as far as we can go with properties of logs. And now let's go ahead and take the derivative with respect to x of the entire equation. So 1 over y times the derivative of y. And on the right side, the derivative with respect to x of all these expressions of x's give us 2 times 1 over x minus 2 times the derivative of x minus 2, which is just 1, minus 1/2 times 1 over x squared plus 1 times the derivative of x squared plus 1, which is 2x. Now let's multiply both sides times y. And we get dy dx equals, so 2y over x minus 2. And then this expression is really just x over x squared plus 1. So we're going to multiply that by y. And now we should need to do our substitution of y. Remember that y was equal to this original expression. Y is equal to x minus 2 squared. So if we put that in, we should be done. Let's make a little room here. Okay. So that black y expression right there in black, next to the 2 over x minus 2. And again, that black y expression right next to the x over x squared plus 1. And we should be able to toggle between rational exponents and roots. All right, well, it looks like we do or don't have common denominators. Looks like we don't. We can simplify an x minus 2 factor here. All right, and then we can get common denominators by multiplying the top and bottom here by x squared plus 1.